Welcome to this first lecture on Fourier transform. Fourier transform is one of the very important transforms in physics. And when we talk of Fourier analysis, we are basically dealing with how we can decompose some signals into sine and cosine waves. And it's very important because we use it in things like spectral analysis. And also we can apply the Fourier analysis in finding the solutions to the differential equations and many other more applications. So I want us to consider how to do the Fourier transforms. And when talk of Fourier transforms, they are categorized as we can have Fourier sine transform, which we will study now. We also have Fourier cosine transform, and then we also have complex Fourier transform. And under Fourier sine transform and Fourier cosine transform, we have infinite and finite. So in this lecture one, you're going to look at the infinite Fourier sine transform. So the infinite Fourier sine transform of a function. So if you have a function f of x, notice that we are using the capital F to represent this. So we are having a certain function f of x with the x in the range of values between 0 to positive infinity. Then its Fourier transform is denoted by, so its Fourier transform is denoted by we are going to use now the small letter f, and then we put here s. S means sine transform of n. Now notice that this was f of x. We are now changing to f of n, where n is a positive integer. So where n is a positive integer, let's say greater than 0, positive integer. So this is how we define it, the formal definition, the definition of this. So if you want to get the Fourier transform of a given function f of x, which we are going to denote by this is how it's supposed to define this. Defined by f of n. So this is a Fourier sine transform of this particular function is equal to the integral from 0 to positive infinity capital F of x sine of nx dx. So this is our first equation, or basically the definition of what you call the infinite Fourier sine transform. So this is a definition of how to get it. And suppose you have been given this fs of n, you already have the transform, you want to get back the function, then we talk about the inverse Fourier transform. So we shall give the definitions and then we shall look at an example on how to handle this. So if you are to get it, you have given the function fs of n and you want to get f of x, we now talk about the inverse Fourier transform. So f of x, which we are going to call the infinite now Fourier transform. This one here, the f of x is now our inverse Fourier sine transform, and it's defined by, so this is how we define it. F of x will be given as 2 over pi the integral from 0 to positive infinity of fs of n sine of n x dn. So this is our second equation. So notice that this is now the definition of inverse Fourier sine transform, while this is the definition for the the infinite Fourier sine transform. So if you want to get the Fourier transform of a given function, the function will be the f of x function. So if you get its Fourier transform, then that is be denoted by the letter fs of n. Now, if given already the transform and you want to get the original function, then we can do the inverse Fourier transform, and that is what is defined by this definition. So to get f of x, which is the inverse Fourier transform, sine transform would be 2 over pi from 0 to plus infinity f of s fs of n sin nx dn. So those are the formal definitions which we are going to use in working out an example. So we can generally say thus we can say that if you have fs of n, this one here is basically what you're calling the Fourier transform of the function f of x, like that. So to get this, just do a Fourier transform of this f of x to get this. And similarly, to get this other function here, f of x, they just need to do a Fourier inverse transform of the given function here, fs of n. So just forward or backward, like that. So fs, this one here, this f of s here, is a symbol for Fourier sine transform, while this other one here, fs inverse, is the inverse Fourier sine transform operators. So to underscore this more, let's look at an example of how to work out this. So let's have an example. So example is here. Find the infinite Fourier sine transform of, so you can have a function, for example, e raised to power negative x. So how would we evaluate this? So the first thing, you begin from the definition. So we have that the given function f of x in this case is e raised to power negative x, and we are looking for its Fourier transform. So this is what you are looking for. So we are going to begin by putting up the definition of a Fourier transform for the sine. So if we do that, we are going to say that from the definition of the infinite Fourier sine transform, we have that fs of n is supposed to be given by the integral positive infinity of f of x, then sine of nx dn, like that. And notice that our f of x here is the given function, so we can write that this is similar to having fs of n integral 0 to infinity. Our f of x, we now substitute the given function, which is e raised to power negative x. Then we now proceed and write sine nx dx. This is supposed to be dx, sorry, this is dx, this should be dx, like that. So we need to evaluate this integral. For us to be able to get the Fourier transform, we need to evaluate this integral. If we check this integral, we can do it by using integration by parts. We can evaluate using integration by parts. So evaluation of this integral and the solution to this is in our second lecture 2, where we're going to evaluate this example using the integration by parts method. So see you in lecture 2 so that we can work out this example, whereby we're going to let this side here, if you call that to be u, and this other one here will be dv, and then we can evaluate and find the value. So next lecture.